Today I want to discuss in this lecture the another resources, renewable resources like magneto-hydrodynamic power generation. In this lecture I want to discuss the introduction to magneto-hydrodynamic power, principles of MHD power generation, MHD cycles and working fluids, types of MHD generator, features of MHD systems, advantages and disadvantages of the MHD power generation. The MHD means the magneto-hydrodynamic, and the MHD power generation means magneto-hydrodynamic power generation. So the magneto-hydrodynamic generator is a magneto-hydrodynamic device that utilizes a Brayton cycle, transforms the thermal energy and the kinetic energy into the electricity. The Brayton cycle is a thermodynamic cycle named after George Brayton that describes the workings of a constant pressure heat engine. The original Brayton engines used a piston compressor and piston expander, but more modern gas turbine engines and the air-breathing jet engines also follow the Brayton cycle. Although the cycle is usually run as an open system, it is conventionally assumed for the purposes of the thermodynamic analysis that the exhaust gases are reused in the intake, enabling analysis as a closed system. The engine cycle is named after the George Brayton, the American engineer who developed it, originally for the use in piston engines, although it was originally proposed and patented by the Englishman John Barber in 1791. It is also sometimes known as the Joule cycle. The reversed Joule cycle uses an external heat source and incorporates the use of a regenerator. One type of Brayton cycle is open to the atmosphere and uses an internal combustion chamber, and another type is closed and used a heat exchanger. MHD generators are different from the traditional electric generators in that they operate without moving parts. There is no turbine to limit the upper temperature. They therefore have the highest known theoretical thermodynamic efficiency of any electrical generation method. MHD has been extensively developed as a topping cycle to increase the efficiency of the electric generation, especially when the burning coal or the natural gas. The hot exhaust gas from an MHD generator can heat the boilers of a steam power plant, increasing the overall efficiency. An MHD generator, like a conventional generator, relies on moving a conductor through a magnetic field to generate the electric current. The MHD generator uses hot conductive ionized gas, which is called plasma, as the moving conductor. The mechanical dynamo, in contrast, uses the motion of mechanical devices to accomplish this. Practical MHD generators have been developed for the fossil fuels, but these were overtaken by less expensive combined cycles in which the exhaust of a gas turbine or molten carbonate fuel cell heats the steam to power a steam turbine. A combined cycle power plant is an assembly of heat engines that work in tandem from the same source of heat, converting it into the mechanical energy. On land, when used to make electricity, the most common type is called a combined cycle gas turbine plant, that is called CCGT plant. Combined cycle gas turbine plant. The same principle is also used for the marine propulsion, where it is called a combined gas and steam plant, that is called COGAS plant. The combining two or more thermodynamic cycles improves the overall efficiency, which reduces the fuel cost. The principle is that after completing its cycle in the first engine, the working fluid is still hot enough that a second subsequent heat engine can extract the energy from the heat in the exhaust. Usually the heat passes through a heat exchanger so that the two engines can use different working fluids. By generating the power from multiple streams of work, the overall efficiency of the system can be increased by 50 to 60%. That is, from an overall efficiency of say 34% to as much as 64%. This is more than 84% of the theoretical efficiency of a Carnot cycle. This can be done because the heat engines can only use the part of the energy from their fuel which is less than 50%. In an ordinary, that is called non-combined cycle heat engine, the remaining heat such that the hot exhaust gas from the combustion is wasted. MHD dynamos are the complement of the MHD accelerators which have been applied to the pump liquid metals, seawater and the plasmas. Natural MHD dynamos are an active area of the research in plasma physics and are of the great interest to the geophysics and the astrophysics community, since the magnetic fields of the earth and the sun are produced by these natural dynamos. The concept of MHD power generation was introduced for the very first time by the Michael Faraday in the year of 1832 in his Bakerian lecture to the Royal Society. He in fact carried out an experiment at the Waterloo Bridge in Great Britain for measuring the current from the flow of the river Thames in Earth's magnetic field. This experiment in a way outlined the basic concept behind the MHD generation. Over the years, then the several research work had been conducted on this topic, and later in August 13, 1940, this concept of magneto-hydrodynamic power generation was imbibed as the most widely accepted process for the conversion of heat energy directly into the electrical energy without a mechanical sublink. The principle of MHD power generation. The principle of MHD power generation is very simple and is based on the Faraday's law of the electromagnetic induction, which states that when a conductor and a magnetic field moves relative to each other, then the voltage is induced in the conductor which results in flow of current across the terminals. The Faraday's law states that a current will be induced in a conductor which is exposed to a changing of the magnetic field. Lenz's law of the electromagnetic induction states that the direction of this induced current will be such that the magnetic field created by the induced current opposes the initial changing of the magnetic field which produced it. The direction of this current flow can be determined using the Fleming's right-hand rule. This rule states that hold out the right hand with the first finger, second finger and the thumb at the right angle to each other. If the forefinger represents the direction of the line of force, the thumb points out in the direction of motions and the applied force, then the second finger points in the direction of the induced current. So the first finger, second finger and the thumb at the right angle to each other. First hold it in the right hand. If the forefinger represents the direction of the line of force, then the thumb points in the direction of motion or the applied force and the second finger points in the direction of the induced current. The Faraday's law of induction explains the working principle of the transformers, motors, generators and the inductors. The law is named after the Michael Faraday, who performed an experiment with a magnet and a coil. During the Faraday's experiment, he discovered how the EMF is induced in a coil when the flux passing through the coil changes. As the name implies, the magneto-hydrodynamic generator shown in the figure below is concerned with the flow of conducting fluid. This is in the presence of the magnetic and the electric field. This is the magnet and this is the electric field. So electric field and magnetic fields are created in this region. In the conventional generator or the alternator, the conductor consists of the copper winding or the strips, while in an MHD generator, the hot ionized gas or the conducting fluid in the conventional generator or the alternator, the conductor consists of the copper windings or the strips, while in the MHD generator, the hot ionized gas or the conducting fluid replaces the solid conductor. A pressurized electrically conducting fluid flows through a transverse magnetic field in the channel or the duct. This is the channel or the duct. This is the segmented electrodes which creates the electric fields, and these are the two magnets or solenoids. It creates the magnetic field. So in this duct or the channel, the electromagneto-hydrodynamic fields are created. Pair of electrodes are located on the channel walls at the right angle to the magnetic field and connected through an external circuit to deliver the power to a load connected to it. Electrodes in the MHD generator perform the same function as the brushes in a conventional DC generator. The MHD generator develops the DC power and the conversion to AC is done using an inverter. power generated per unit length by the MHD generator is approximately given by the P is equal to sigma U B square by P, where the U is the fluid velocity, B is the magnetic flux density, sigma is the electrical conductivity of the conducting fluid, and the P is the density of the fluid. It is evident from the equation above that for the higher power density of an MHD generator, there must be a strong magnetic field of 4 to 5 Tesla and high flow velocity of conducting fluid besides the adequate conductivity. The MHD cycles can be of two types, that is the open cycle MHD and the closed cycle MHD. Now I will describe the different types of MHD cycles and the working fluids in the open cycle MHD and the closed cycle MHD. The open cycle MHD system shown in the figure. In the open cycle MHD system, the atmospheric air at very high temperature and pressure is passed through the strong magnetic field. Coal is the first processed and burnt in the combustor at a high temperature of about 2700 degrees centigrade and pressure about 12 atmospheric pressure with preheated air from the plasma. Then a seeding material, this is the seed recovery. So a seeding material such as potassium carbonate is injected to the plasma to increase the electrical conductivity. The resulting mixture, having an electrical conductivity of about 10 Siemens per meter, is expanded through a nozzle. This is the nozzle, so as to have a high velocity and then passed through the magnetic field of the MHD generator. During the expansion of the gas at high temperature, the positive and negative ions move to the electrodes and thus constitute an electric current. Electrodes channel provided electric contact between the flow and the external load. The power output is DC and it is necessary to use to change it to an AC before the power can be fed to an electric grid. So this is the inverter. The gas coming out of MHD generator is still sufficiently hot and is used to raise the steam, which generates the additional energy in a steam turbine alternator unit. Since the same air cannot be reused again, hence it forms an open cycle and thus is named as the open cycle MHD. A part of this steam is also used in a steam turbine which drives a compressor for compressing the air for the MHD cycle. The seed material is recovered from the gas. The harmful emission of sulfur are also removed from the gas before it is discharged to atmosphere through a stack. This is the seed recovery systems and this is the removal of nitrogen and sulfur system, and finally it is discharged to the atmosphere through the stack. Now come to the closed cycle MHD system, which is shown in the figure. The closed cycle inert gas MHD system was conceived in 1965. The main disadvantages of the open cycle system is very high temperature requirement and a very chemically active flow could be removed by the closed cycle MHD system. As the name suggests, the working fluid is closed cycle is circulated in a closed loop. The working fluid is the helium or the argon with the cesium seeding. Figure shows a closed cycle MHD system. The complete system has three distinct but interlocking loops. On the left is the external heating loop. The coal is gasified and the gas having a high heat value of about 3.35 megajoule per kg and temperature of about 530 degrees centigrade is burnt in a combustor to produce the heat. The heat exchanger HX, this heat is transferred to the argon, the working fluid of the MHD cycle. This is the heat exchanger. The combustion products, after passing through the air preheater to recover a part of the heat of the combustion product, and the purifiers to remove the harmful emissions and discharge to the atmosphere. The loop in the center is the MHD loop. The hot argon gas is seeded with the cesium and passed through the MHD generator. The DC power output of the MHD generator is converted to AC by the inverter. This is the inverter, and is then fed into the grid. The loop shown on the right hand side in the figure is the steam loop for further recovering the heat of the working fluid and converting this heat into the electrical energy by the generator. The fluid passes through the heat exchanges HX2 where it imparts its heat to the water, which gets converted to the steam. This steam is used partly for during a turbine which runs the compressor, partly for the turbine driver and alternator. The output of the alternator is also to the grid. The working fluid goes back to the heat exchangers after passing through the compressor and the intercooler. A closed system can provide more useful power conversion at lower temperatures around 900 degree Kelvin as compared to the 2500 degree Kelvin for the open cycle system. Now come to the types of the MHD generator. The Faraday MHD generator. The Faraday generator is named after the man who first looked for the effect in the Thames River. A simple Faraday generator would consist of a wedge-shaped pipe or the tube of some non-conductive material. When an electrically conductive fluid flows through the tube in the presence of the significant perpendicular magnetic field, this is the electromotive force and the load currents. This is the Faraday and the Hall electric fields in this plane, and this is the motion, and this is the field. Both are in 90 degree to each other. When the electrically conductive fluid flows through the tube in the presence of a significant perpendicular magnetic field, a voltage is induced in the field, which can be drawn off as the electrical power by placing the electrodes on the side at 90 degree angles to the magnetic field. There are limitations on the density and the type of the field is used. The amount of power that can be extracted is proportional to the cross-sectional area of the tube and the speed of the conductive flow. The conductive substance is also cooled and slowed by this process. MHD generators typically reduce the temperature of the conductive substance from plasma temperatures to just over the 1000 degrees centigrade. The main practical problem of a Faraday generator is that differential voltages and the currents in the fluid shot through the electrodes on the side of the duct. The most powerful burst is from the Hall effect current. This makes the Faraday duct very inefficient. Most further refinements of the MHD generators have tried to solve this problem. The optimal magnetic field on the duct-shaped MHD generator is a sort of saddle shape. To get this field, a large generator requires an extremely powerful magnet. These are the duct-shaped MHD generator. These are the electrodes, and these are the insulator spaces. The fields is created like this. This is the isolated loads. Insulator wall is this. The hot gas flow through this duct shaped channel. The many research groups have tried to adapt the superconducting magnets to this purpose with the varying of success. Now the second type of generator is called the Hall MHD generator. The typical solution historically has to use the Hall effect to create a current that flows with the fluid. This design has arrays of short segmented electrodes on the side of the duct. These are the electrodes. The first and the last electrodes in the duct power the load. This is the first and the last electrodes in the duct power the load. Each other electrode is shorted to an electrode on the opposite side of the duct. These shorts of the Faraday current induce a powerful magnetic field within the fluid, but in a core of a circle at right angles to the Faraday current. This secondary induced field makes the current flow in a rainbow shape between the first and the last electrodes. Losses are less than a Faraday generator and voltages are higher because there is less shorting of the final induced current. However, this design has problems because the speed of the material flow requires the middle electrodes to be offset to catch the Faraday currents. As the load varies, the fluid flow speed varies. Misalignment of the Faraday current with its intended electrodes and making the generator's efficiency very sensitive to its load. The last type of MHD generator is the Dix MHD generator. This is the third and currently the most efficient design is the Hall effect Dix generator. This design currently holds the efficiency and energy density record for the MHD generation. The Dix generator has the fluid flowing between the center of the Dix. This is the fluid, center of the Dix, and the duct wrapped around the edge. The magnetic excitation field is made by a pair of circular Helmholtz coil above and below the disc. The Faraday current flows in a perfect dead shot around the periphery of the disc. This is the Faraday current. The Hall effect currents flow between the ring electrodes These are the Hall electrodes to the Hall currents. The Hall effect currents flow between the ring electrodes near the center duct and the ring electrodes near the periphery duct. The white flat gas flow reduces the distance, hence the resistance of the moving fluid. This increases the efficiency. Another significant advantage of this design is that the magnets are more efficient. First, they cause the simple parallel field lines. Second, because the fluid is processed in a disc, the magnet can be closer to the fluid, and in this magnet geometry, the magnetic field strength increases as the seventh power of distance. Finally, the generator is compact for its power, so the magnet is also smaller. The resulting magnet uses a much smaller percentage of the generated power. Now the features of the MHD system. For the efficient practical realization, a MHD system must have the following features. Number 1, the air superheating arrangement to heat the gas to around 2500 degrees centigrade so that the electrical conductivity gas is increased. The combustion chamber must have the low heat losses. A management to add a low ionization potential seed material to the gas to increase its conductivity. A water-cooled but electrically insulating expanding dust with long life electrodes. A magnet capable of producing high magnetic flux density. Seed recovery apparatus necessary for both the environmental and the economic reasons. The MHD generation have some advantages and the disadvantages. Now come to the advantages. The conversion efficiency of a MHD system can be 50% as compared to the less than 40% for the most of the efficient steam plants. Large amount of power is generated. It has no moving parts, so more reliable. It has ability to reach the full power level as soon as started. Because of the higher efficiency, the overall generation cost of the MHD plant is less. The more efficient heat utilization would decreases the amount of heat discharged to the environment, and the cooling water requirements would also be lower. The higher efficiency means the better fuel utilization. The reduced fuel consumption would offer the additional economic and the social benefits. The closed cycle system produces the power free of pollution. Now come to the disadvantages of the MHD generation. The MHD systems suffer from the reverse flow such that the short circuits of the electrons through the conducting gases around the ends of the magnetic field. These are the total discussion on the magneto-hydrodynamic power generation. These are the references from where I make this lecture. You should go through these references for gathering the more knowledge. Thank you.